We're going to take a look at two different topics that we're going to kind of meld into one. The first being how to find rational roots of a polynomial, and then the second one being the fundamental theorem of algebra. So let us go ahead and start with that first topic, so finding rational zeros. Our goal is, given a polynomial function, not just to find all the zeros, we're going to get to that in a second, but just how to find the rational zeros. So really quick, to kind of maybe remind ourselves what it means to be a rational number. And so what a rational number is just a number that can be written in the form of p over q, where both p and q are integers. Okay, and so for example, these are all the numbers that aren't irrational, that are real. And so for example, 1/3 is a number that when I write it as a decimal approximation, it just goes on infinitely, but it repeats. This is about equal to 0.333, and so on. Versus numbers like pi, on the other hand, they're roughly equal, 3.14159, and so on, but it doesn't repeat. So I'm just looking for the rational zeros. I'm not looking for anything irrational. I'm not looking for anything complex either. All right. So what the rational root theorem says is that if I have a polynomial of this form here, then it'll be the case that all the rational factors will be of the form p over q, where p is one of the factors of my constant, and q is one of the factors of my leading coefficient. So we've kind of discussed this before, or if I had a, I don't know, just make something up really quick, x to the third plus 2x squared minus 5x plus 6, we knew that if we were to factor this into solutions, if this does factor, which I don't know that it does, it would have to factor into something like this. And so A, B, and C will all multiply together to give me 6. So that means they have to be factors of 6. Now we're adding in this additional kind of loop, and that is that, well, what if I have a coefficient on my lead term that is not 1? And so that kind of throws things off, and so now that's where we get our rational root theorem that says that, well, really the potential factors here are a factor of my constant over a factor of my lead coefficient. So let's go ahead and look at an example and make a little bit more sense of this. So let's look at these two. So the first one is something that we've kind of seen before. So what are the potential factors here? Well, there is no lead coefficient, and so, well, there is, it's 1. And so my potential factors are going to be, well, either positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, positive negative 6, and positive or negative 12. So it's all the factors of this number right here, okay? And so then, of course, these are all over 1 over 1 over 1 over 1, because those are my, that's my coefficient, the only factor of my lead coefficient. And so that's not super interesting. We've talked about this before, but this problem over here, there's a little bit more to it. So my potential numbers that would go in the top of my fraction are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And then my potential denominators are plus or minus 1, plus or minus 2, and plus or minus 4. And so what I end up getting is there's going to be some potential rational zeros here. And so what they're going to be is, well, let's take all the numbers over 1. So that would just be, well, everything we had before, plus or minus all of these. So let's write those out real quick. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And then I can have all these numbers over 2. So I can have plus or minus 1/2. 2 over 2 is just 1, so that's not interesting. Plus or minus 3 over 2. 4 over 2 is just 2. We already have that. 6 over 2 is just 3, I already have that, and 12 over 2 is just 6, I already have that. So then I can put these over 4, so I have plus or minus 1/4. 2 over 4 is just 1/2. I have 3/4, plus or minus 3/4. And I have 6/4, which is 3/2. I already have that. Oh, 4 over 4 is 1, of course, and 12 over 4 is 3. Okay, so the thing is that this is getting dangerously close to just guessing and checking, but that's fine. And these are all my potential factors. I'm not guaranteeing you that any of these are factors. I'm just saying these are the potential ones to check. If there are factors of this, if there are zeros of this polynomial here, they're going to come from this list if they're rational. Now, the interesting thing is, of course, if we graph this function, there are no rational zeros. In fact, they're all imaginary, so none of these work, which seems kind of, like a big waste of time. And it kind of is, because we have some other tools available to us that are going to help us out. But this is just a good thing to know that, hey, my list of factors my list of zeros have to come from here, have to come from this group. Okay, so let's actually see how this is going to help us out when I look at another example here. Let's see, what did I just have up? Did I have this up? Yep, that's what I just did. And okay, so let's look at an example here. So let's find all the real zeros of this. So x cubed minus 8x squared plus 11x plus 20. So my possible rational zeros are, well, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, and then just 10 and 20. Okay, so these are all my potential rational zeros here. And you'll notice they're all whole numbers because my coefficient on x cubed was just 1. So now I can just start plugging these in. I could either just plug these in, or I could also use our new tool that we've learned recently, which is synthetic substitution. So let's go ahead and maybe try a couple of these and just see what we get. So if I have 1, -8, 11, and 20, this is dangerous because I'm probably going to make a mistake somewhere, but that's okay. All right, so this is 1 and 1 and -7 and -7 and 4 and 4 and 24. Okay, so that was no good. Let's try -1, 8, 11, and 20. Okay, so -1 gets me 1. This is -1, so -9, which is 9 and 20. Oh, this one did work. Okay, and 0. So what I can do, so you'll notice I'm not using a calculator at all. I can do this all by hand, and so now I know that, well, x plus 1 is a factor here. And so I can rewrite this function as f of x is equal to x plus 1, because this is the factor since -1 is a 0. And what's left over is x squared minus 9x plus 20. And the great thing is that I actually can factor that myself. And you'll notice that the things it's going to factor into are x minus 4 and x minus 5, of which 4 and 5 were, of course, a couple of our options here. So without using a calculator, I was able to factor this not too bad. However, of course, I do have that calculator available to me, and we're going to see how it's going to be useful here in a little bit. So there you go. Found all the real zeros. I guess I should actually list them. -1, 4, and 5. Okay. Let us look at the next thing then. So this is going to lead us into talking through what's called the fundamental theorem of algebra. And so the point being is that was great. I could find the rational zeros without too much effort. Now let's try and find all the zeros. That's going to be my goal. So while we're working through this next section, we're going to try and find all the zeros of a polynomial. Okay, so let us go ahead and discuss what the fundamental theorem of algebra says. So it kind of comes in two parts, which are kind of confusingly stated, but I'm going to sum it up for you here in a second. So what it says is, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of the complex numbers. Now, to be clear, when I say the complex numbers, what I'm talking about is, so the complex numbers are of the form a plus bi. Now, a doesn't have to necessarily be anything but 0, and b doesn't have to be anything necessarily but 0. And so what that means is that, for example, the number 2 is in the set of complex numbers. It's just it can be written as 2 plus 0i. So what this is saying is that if I have a polynomial where n is greater than 0, the degree, this equation f of x equals 0 has to have at least one solution in the complex numbers. Okay, great. If f of x is a polynomial of degree n where n is greater than 0, the equation f of x equals 0 has exactly n solutions. So not only does it have at least one, it has exactly n solutions. And what we mean by that is, and maybe the first part should say really distinct solutions, it means that there have to be n different factors of my polynomial. And so in different zeros, it just might be the case that some of those are repeated. So we've talked about the fact that I can have a double root, for example, of an equation, or even a triple root of a polynomial function. And so if I add all those up, what I will always get is that an nth degree polynomial will have exactly n zeros when I take into account those double or triple countings or quadruple or whatever it is. So let's go ahead and take a look at that and see how we can use it to our advantage. So my goal is to find all the zeros of f of x. So I have this big equation here. So I am going to use my resources to help me out. And one of those resources is my ability to graph. And so the issue is that, well, I guess this isn't too bad. Maybe it's not too bad. Actually, you know what? I'm not even going to graph this one. Let's take a look at how I could do this without graphing. Because this one's not too bad because it's negative 14 down here. So my possible rational zeros are, well, plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. So that's really not that bad. Let us go ahead and try some synthetic substitution to try to find out which one of those is actually the case. Maybe I'll get lucky here. Let us start with negative 1. Let's start with negative 1. So I got 1, negative 4, 4, 10, negative 13, and negative 14. Okay, so what I've got here is negative 1, so it's negative 5. It's 5, 9, negative 9, and 1, negative 1. Oh boy, got lucky on my first one. Wait, no, I didn't. No, I just can't add. Gosh darn. How do I undo? There we go. 14. There we go. 14, 0. Okay, so negative 1 is one of the is one of the zeros, so x plus 1 is one of the factors. So let me go ahead and rewrite this as f of x is equal to, and then let's see, I'm going to have x plus 1, and then what's left is, let's see, I'm going to have x to, so this is to the constant, second, third, fourth, wait a second, constant, second, third, fourth, fifth. What did I do wrong here? Oh, because I missed my linear term. Constant, first degree, second, third, and fourth. Oh, well. Okay, so this is x to the fourth. That was embarrassing. Minus 5x to the third, plus 9x squared, plus x minus 14. Okay. So I can do the same thing again now, and actually it hasn't changed what my potential factors are. And so what I'm going to do is, let's see, what number do I want to try out? Do I want to try and get lucky again with this? Let's try. I think, man, I'm trying to remember how we did this. I think 7. I'm feeling pretty confident about 7. Let's try 7. Okay. So if I try 7, let's go with 1, negative 5, 9, 1, and negative 14. If this doesn't work, I'll probably have to break out a calculator and pretend like I just did it myself. This is 1, and this is 7. And so this is 2, and this is 14. This is not promising. This is very much not promising. Yeah, it's not going to work out. How about, maybe was it -7? Come on, -7. Let's see. So 1 and -7. So let's, oh, this, nope, that's not going to be good either. I have no idea what -12 is. Should I? No. Okay, it's not going to be that. Let's try instead. Let's try 2. I feel more confident about 2. Oh, what was this? 14. 2. Okay, so if I try 2 instead, I have 1 and 2, and so that's -3, -6, that's 3, 6, that's 7, and 14. That one did it. Okay, so that's one of my other factors here, is x minus 2. So f of x equals x plus 1 times x minus 2. And then what's left over is x to the, okay, so let's do this right, constant, linear, 2 and 3. So x to the third minus 3x squared plus 3x plus 7. Okay, great. So now I'm getting really close. My factors are, well, so here's the interesting thing. And so I have to really think of why this is the way that it is. I'm down to 7 now. So that means that my potential rational roots are only plus or minus 1 and plus or minus 7. But we just figured out that 7 was no good for positive or negative. And so the interesting thing is that I actually have a double root here. The other root is x plus 1 again. So let us go ahead and do this one more time. 1, -3, 3, and 7. And we're going to find that, I hope, this is going to work out for me. So -1, and this is -4. So this is 4 and 7, -7. There, perfect. So I was able to figure out what all my rational roots are. Now, in reality, would this taken me longer if I didn't remember this problem from before? Yeah, probably. But I'm just trying to prove the point here that, hey, we can do this without a calculator. Next one we'll definitely use a calculator for, and we'll graph it, and it'll make our lives a lot easier. Okay, so I get down to this. And so I think we're going to look at this for a little bit and realize that this definitely does not factor. And so we're very close to finding all the potential roots. And so the one last thing that we can do is, of course, use the quadratic formula here. So if I want to solve just this portion, figure out what the zeros of just this portion is, I can use the quadratic formula. So I can do that. So this is going to be the opposite of b, 4 plus or minus square root b squared 16 minus 4 times 1 times 7 all over 2, which is equal to 4 plus or minus, okay, so this is 28, so -12, which is going to simplify to be 2I root 3 all over 2, which then simplifies one more time to be 2 plus or minus I root 3, I hope. Okay, so what I've done now is found all my zeros. They are -1, -1 again, 2, 2 plus I root 3, and 2 minus I root 3. These are all my zeros of this function. And so this is not proof of, but just an example of the fundamental theorem of algebra. And that I will always have 5 roots here. Now they might be doubled up, they're not all necessarily distinct, as this is the case, and they might not all be real, but I have 5 roots of this polynomial. And so we will do one more. Okay, so let's say I have this one, and let's say I don't want to go through that whole process again. So what can I do to kind of help me out? And the answer is I can use my graphing calculator. So let me go ahead and do that. Let's see, where is GeoGebra at? All right, there we go. And we'll get rid of the drawing space. Perfect. So I'm going to type in my function. So this is going to be f of x is equal to x to the 5th minus 2x to the 4th plus 8x squared and minus 13x and plus 6. Okay, so this is my function. And so what I can see here is that I've got a few roots. I've got one here at -2, and it looks like I have a double root here at 1. And so that tells me that the factors of this are going to be x plus 2, and then it looks like I have 2 of x minus 1, which is perfect. And so I'm going to go ahead and swap back and use this to my advantage. So I don't have to actually go through this whole process of guessing again. I can use my graphing calculator, and the great thing is that, or not the great thing, but the thing is that it doesn't tell me all the roots. It only tells me 3 of them. So I know that this is going to be of the form, let's see, f of x is equal to, so what did we say? X plus 2 times, and then we've got x minus 1, that quantity squared, and then times, and then something. We'll find out what that is here in a second. Okay, so how do I want to do this in the fastest way possible? I'm thinking I could divide each of these out individually, and that sounds kind of like a pain. Let's actually, I don't think it will be that bad. Let's go ahead and see. I'm going to kind of cheat, and it's going to look messy, but that's okay. All right, so the first one I want to take out is -2, and I guess there's a lot of room for error, though, I guess. We'll see. -2, 0, 8, -13, and 6. Okay, so let's go ahead and knock this out. So I've got 1, -2, so -4, this is 8, 0, -16, or that's a, no, oh my gosh, that was all wrong. Okay, 8, -16, so this is -8, and this is 16, and I've done something wrong. No, it's not, it's good. -6, I need to have more confidence in myself. Okay, great. So this is what I'm left over when I divide out the x plus 2. So I'm just going to leave everything there and do this again, but for 1 this time. So I got 1, and -3, and -3, and 5, and 5, and -3, and -3, and 0. Nice. And I'm going to do this one more time. And this is going to be 1. So we got 1 again, and 1, and -2, and -2, and 3, and 3, and 0. Okay, marvelous. And so what we have is we factored this into using my graphing calculator to find my roots, and then using my synthetic substitution to divide these all out. What I've got is f of x is equal to x plus 2 times x minus 1 squared times x squared minus 2x plus 3, which does not factor. And so I'm going to use my quadratic formula to solve just this part here. So this is going to be the opposite, b 2 plus or minus square root b squared. So 4 minus 4 times 1 times 3. Something seems off. No, that's right. All over 2. And so this will simplify to 2 plus or minus. Okay, so this is 4 minus 12, so that's 8. So this is 2I root 2 all over 2, which of course just simplifies to be 1 plus or minus I root 2. Sure. All right. So now all my factors, or all my zeros, are going to be -2, 1, 1 again, and I have 1 plus I root 2, and 1 minus I root 2. Okay, those are my 5 factors, which is exactly what I should have because it's of the 5th degree. The last thing I'll point out, and which is what we're going to be moving to next, is the notice here that I've got all these numbers, which is great, but then I have these two. And so these two have a special relationship. They are called conjugates of each other, and what we've noticed so far is that whenever I have an imaginary number, or an irrational number for that matter, that their conjugate is always the other root. And so that's going to be important later on. But that was a brief run through, let's see, 25 minutes. Okay, not that brief. But run through of how to find rational zeros, and then also how to use the fundamental theorem of algebra, which tells us that polynomials have the same number of zeros as their degree. How to use both of those to find all my zeros. So that's going to lead us into something we can build off of later, but will continue to help us, solve these polynomial functions.